This video is on potential energy in electric fields, the potential and potential differences. And it's partly inspired by the excellent open source book University Physics 2, Thermodynamics, Electricity and Magnetism, which is published under OpenStax. And it's an open source license, a Creative Commons, so we can use this material for free. And chapter 7.3, so you see this covers pretty much the stuff we want to discuss also in electrical energy, so in electrical engineering. And the chapter I was inspired by is the electric potential and potential difference of this particular book. And I prepared a QR code for you so that you can immediately access this book chapter. But I'm explaining these things in my own way, so I'm deviating a little bit from this. But anyway, it's a very excellent, very good source, and I recommend to do the exercises in this book. Okay. So when we have two parallel metal plates, right? Let's say we have two metal plates in a distance, and they are not charged yet, right? So we have two metal plates, so they're not charged yet, they are neutral. And but now we start to move electrons, let's say from one plate to the other, right? So we are now moving maybe an electron or something, or maybe a general electric charge from one plate to the other, which means we are the total charge of both plates does not change, right? But the distribution would change. So after some time, we would accumulate here negative charges on this side, and we would have positive charges on the other side, right? Because when we are moving a negative charge from here, when we are displacing this negative charge, then a positive charge remains. So we have as many negative charges on this plate as we have positive charges on the other plate. So that causes an electric field pointing from positive charges to negative charges, and we would have here a nearly homogeneous electric field, which means it doesn't so within the plates or in the center of the plates, the electric field would be really parallel, and at each point in this inner compartment here, the electric field would be the same. So same strength, same direction, right? But I'm just representing the electric field for now with this one arrow. So, and it is known that when we have a negative charge already here, it's getting more and more difficult. You have to apply more and more force, basically, to drive another electron from here, or another negative charge from here, to the already negatively charged plate. Because this becomes more and more negative, this becomes more and more positive, the electric field gets stronger and stronger, and it basically counteracts your action, right? By moving particles or charges from one side to the other, it's getting more and more difficult the more charges you have. So now let's investigate how much work we would have to apply for a given situation, maybe like this, right? There is already an electrical field established, and we want now in this electrical field, and let's assume this is now constant, and even if we change a little bit the charge, right, by moving a charge from here to this side or another one to that side, we assume that the electric field doesn't change when we, for now at least, when we move a particle here from one side to the other, right? So the work we have to do, we have to apply to a certain charge, to move a charge from one place to another in an electric field, let's say from point A to point B, is the electric force exerted on the charge, so times a little vector which is on a path basically of motion, right? From that path describes from where we start and where we end. So let's say we start, let's have a look at maybe an electron, right? So no, let's say a positive particle, right? The positive particles don't want to go to this side, or positive charges, right? Because this is already positively charged, so we have to overcome a repelling force, right? So this counteracts basically the motion of a positive charge. So, but now let's assume we are moving from this, a charge moving from this point A, let's say on this plate, maybe to this point B here, right? And so maybe it can be a straight line, can be any line, right? But let's use a straight line because it makes the discussion a bit easier. And this dashed line is basically what we call the path S. So we want to go from A to B, and we have a charge, let's say a positive charge, right? So because we want to move now a positive charge from this metal plate to another one which is already positively charged, right? And of course there will be a force exerted on this charge by the electric field which is already there. And we said that this negative sign is basically the fact that when the displacement ds is acting against the force, so when it's antiparallel, then this scalar product becomes negative. So with this negative, it becomes positive. So that means if, for example, F is pointing, let's say, downward, right, and ds is pointing upward, and let's say they are perfectly antiparallel, then you know that from the scalar product, let's say F ds, that would be the length of S, so the amount, the field, the force, times the length of this little displacement, times the cosine between these two vectors, right? Let's say F pointing downwards, ds pointing upwards. Then in this case, it would follow that the cosine of alpha is -1, because the angle between these two vectors here is 180 degrees, and the cosine of 180 degrees is -1. So that means in the end, for this particular case, we would have F times ds, right? So now I'm expressing the absolute value of F, so the norm of this vector, the length of this vector just by F, and leaving out this vector arrow here, right? So F is then the amount, the length of the vector, and this ds is the amount of the vector ds, right, times -1, right, from the cosine alpha. So that means in this particular case, you see that this product would be less than 0. It's a scalar product, which means the result in the end is a scalar. So this product here, for this particular case, would be negative. With this negative, it would be positive. And that's according to our convention, which means we are doing work on the system. So when we are doing work on the system, we want the work, so this is the definition, right? We want this to be greater than 0, right? Greater than 0. Maybe let me rewrite it. So W greater than 0, right? So that is, we are doing work on the system. If the work is done by the system, so for example, when you release now, let's say a negative particle, a positive particle from this plate, metal plate, charged metal plate, it would be repelled by this positive charge, and it would be attracted by this negative charge here. So then this potential energy, which it basically in fact would have, would then be transformed to a kinetic energy, and then the system releases energy, and the work which is then done by the system is counted negative. Because we will discuss this a little later, why we want this to be. So doing work on the system and work done by the system. So when the system releases energy, right, when it does work and changes the outer world, we say, that's our definition, right? It's a definition. So we want this to be negative and we want this to be positive. And we have good reasons for that, but we will come to this a little later. Okay, so where is now, so we now have the path ds here. The path S, and this path is now made of small steps, right? Let's say the positive charge is somewhere here at this location, and this is the vector ds. And that can be basically separated in the vectors dx parallel to the x-axis, so we have to introduce a coordinate system, and dy parallel to the y-axis, right? So let me write this again. So we have a coordinate system, a right-handed coordinate system, where we have, of course, in 2D you don't have a right or a left-handed coordinate system. Okay, so x and y are oriented like this, but this is our definition. Okay. And so that means we can, and then we have this displacement vector. So let me draw it a little larger. So this is our vector ds. And then that can be separated in a component dx, right? And a component dy. In fact, these are not components, but really vectors. So what I mean with this is that we say, okay, this little displacement vector is nothing but the vectorial sum of vector dx and vector dy. So a little displacement in x and a little displacement in y. So to go from here to here, right, I could use this ds as my step, or I could say I want to go first in the direction dx and then in the direction dy. I would end up in the same point here, right? So to go from here to here, I could follow this line, or I could first move along the x-axis and then move along the y-axis. That's what it says. Okay, you see that now the electric field. So let's discuss this scalar product which we need. So basically, why do we need this electric field? I forgot to mention this, right? So when you look at the W, right, the work which is done by us to the system or done by the system to the environment, we have this scalar product between these two vectors, right? So, and first of all, we've seen that the force can be expressed as the electric field acting on a charge, right? So this would be F. So it's the electric field, it's basically the definition of the electric field, right? If you think of Coulomb's law, for example, you can separate one of these charges in the Coulomb's law, and what remains is then the definition of the electric field, and times this little, we sometimes call it even a test charge, because how can we measure an electric field? We could, for example, put a charge, a tiny charge, which does not disturb the electric field too much, into the electric field and measure the force on that test charge in this electric field to characterize basically the force, right? Or to characterize from the force the electric field. So that would be F, right? So now we have the F, then we have still our vector ds with a scalar product in between. Sometimes I use this open circle just to denote, and we want to go from A to B minus. So, okay, now we can simplify the thing a little bit, first of all. So we have then minus Q from A to B, E ds. ds, right? And sometimes I even omit this dot product here, right? So sometimes, so whenever you see something like this, E ds, a product between two vectors, you can assume that this is a scalar product, right? So now let's talk about EDS. Right? E dot ds, in fact. So that's the electric field, and then we are now expressing, or so we are dissecting this vector into two vector components, dx plus dy, right? And you see that this is a kind of associative law, or it is in fact an associative law for scalar products. And so that can now be factorized, or it can be multiplied out in this way. So we know this rule from ordinary numbers, right? But it also applies to vectors, right? It can be shown that this associative law right, also applies to scalar products, right? Scalar product. So you know this from, let's say, classical math, from calculus, that when you say, okay, I have a number, I don't know, 2 times 3 plus 1, then this is identical to 2 plus 3 plus 2 times 1, right? So that's the idea of this associative law, right? And it works. Okay, and from the definition of the scalar product, which we've written down here, right? Maybe I'd write it in a more general way. So let's say if we dot two vectors A and B, then we have the lengths of the vectors, the norm, we call this also the norm, and the cosine, I call this angle alpha, right? So we have one vector A, another vector B, in between is the angle alpha, and you can imagine that, or it's obvious that if these two vectors are perpendicular, right, if A and B form a right angle, so if it's like this, let's say, if this is A and this is B, A, with an angle, with a right angle, which is alpha, right? In this case, alpha would be 90 degrees, and the cosine of this 90 degrees is 0, right? You can also think of the scalar product being a kind of projection of one vector to another one, like a shadow, right? It would shine, or it would create on this plane, right? And if you have the sun coming from here, the illumination is coming from here, then this vector here would not cause any shadow on B, so the scalar product vanishes. So that means if two vectors are, so if, for example, a vector E is perpendicular to dx, which it is, right? If you look at the diagram here, you would see that the scalar product dx would be 0, right? So we can now infer that this is 0. Because of the geometry, only this component here remains. Good. So let me rewrite the formulas on the next page again. So we said we have W is minus Q we go from A to B. So I start with the most general expression. This is always true. So basically not just from A to B, it's, yeah, how do we go there, right? I should have denoted this, yeah, basically along the path S, right? So it would be a bit more precise if I say, I want to walk along this path S, first of all, right? EDS, but in fact, in the end, the path S starts at A and ends at B, right? But this is a bit more, it's a bit clearer. So, and from the geometry we discussed, this can now be simplified to E along dy, along the path. So, now the question is, what is the path S, right? We are now starting from A to B. And when we go from A to B and we're just now integrating in the y direction, then the y coordinate, this dy, which is not a vector anymore, it is a vector, sorry, it would start at this point A and end at this point B, but we are only interested in the y components, not in the x components anymore. We don't have to take them into account. But let's, so first along S. So now let's discuss this E dy. So you see, E is pointing in the negative y direction, whereas dy is pointing in the positive y direction. So E and dy are antiparallel. So E and dy are antiparallel. So when they are antiparallel, we've this already shown, then the scalar product can be simplified, or the result basically is like this, right? It's the field strength times the displacement in y direction times -1 because of the antiparallel orientation of both fields. So from this now follows that W is minus Q along the path S, right, still. And now we are simplifying E dy and just look at the scalar, the remaining scalars of this integral. So, and you can see that now the two minuses cancel, which is now the integral of E dy along the path S. But our assumption is that the electric field is constant, it's homogeneous, right? So it's homogeneous. Homogeneous, that's what we say. Homogeneous means same direction, same field strength in all points here in the area of investigation. Good. So that means we can further simplify this. So under the assumption that E is constant, homogeneous, basically, it follows that W can even that E is basically separable, it's constant, so we can take it out of the integral, and now we just have the integral in y direction along the path S. So the path S is still this dashed line, and we are walking now along this line, but we are just looking at the y. We are not interested in x anymore because the influence in x direction vanishes, right? Because the motion perpendicular to the electric field does not contribute to the work. The scalar product vanishes, right? We do not have to apply any work to move this particle perpendicular to the electric field. So we are not changing its potential energy, as we will see later, right? So it is basically the same in a gravitational field. So when I have my pen and I lift my pen, I do work, and I have to act against the gravitational force. I feel this, right? So my ds pointing upwards, but the force is pointing downwards, right? So I do work. The scalar product of my motion and the electric field is negative. Okay, that means I increase the potential energy by the work I do. My work I do increases the potential energy of this pen, and this pen can now do work. So if I release this pen, it falls back and can take an action, can cause a damage or whatsoever, right? So then the potential energy is then converted to kinetic energy, and it has literally an impact. So then the system is doing work. The work would be negative. The negative work decreases the potential energy of this pen. So, but when I move it from, so ideally, right, without any friction or anything, and we move now the pen from here to here, we would not change its potential energy, right? The scalar product of the gravitational field, and the motion vector is 0, right? Because we are moving along this line, whereas the electric field is the electrical field or the gravitational field is pointing upwards or downwards, so perpendicular, normal to the motion, right? So this component does not contribute. The only one is this component, the component which purely points into the basically parallel or anti-parallel to the electric field. Okay, so, but what does it mean when we go from A to B and we are just looking at the y coordinates? So then you can see that of this path, we start maybe at the integral of this would be then, of course, E, and we are starting at the y component at point A and end at the y component of the point B, dy, right? And, okay, the antiderivative of 1, right? You have a 1 here. 1 times dy is just y itself. So that would be the electric field times yb minus ya, which is E times delta y. Or if we denote the distance of these two metal plates with d, let's use the distance d, then it would be simply E times d. Okay, so this is the work we do to bring positive charge in an electric field. Oh, I forgot the Q. Where's the Q? I missed the Q somewhere. No, this is okay, but here's the Q, of course, sorry. Because here we are just looking at the scalar product of the electric field and the displacement. But here I'm going back to here's Q, here is Q, and that means also here we have a Q and a Q here, and Q here, Q and Q. So again, W for a homogeneous field of bringing a charge Q in the electric field and displace it. So we move it by the distance d parallel to the electric field or anti-parallel to the electric field. And this expression here is acting on a charge, and that's the work we are doing, or which is done by the system. Good. But we can also see that the potential energy, electrical energy, let's call this U, this is basically changed by the work we are doing, right? So this is the potential, the change of the potential energy in the change of a potential energy of a charge in an electric field when we move it against the field or with the field, right? So, and again, if W is negative, it's equivalent with delta U is negative, right? Which means the system, the work is done by the system, work done by system, or the work is done on the system. That's what we are currently discussing, work done on system. Then W is our work which we add to the system, which means we are, with our work, we are increasing the potential energy, right? Like with the pen. I have the pen in the gravitational field, I do work, and with this work, I increase the potential energy. So the change in potential energy is the work we are doing in this case to the system, right? So done by the system or done on the system. So we are doing the work and then it's positive. And this is the reason why this negative here makes sense, right? Otherwise, this would be different. And delta U would be basically be negative W. And this is, yeah, you can do it. But for me, it's more intuitive if we use this convention. Okay, so now the question is this true for both kinds of charges, right? What happens when we move a positive charge, right? A positive charge against an electric field, right? So we start at an already negatively charged plate, and we are displacing even more, even one positive charge more, which would also make this more negative. So, but that requires work, right? We have to act against the force which is acting in the opposite direction. Would this also work with negative particles or negative charges, right? Let's discuss this. Okay. Of course it does, right? But let's show it. And I want to show this again with the same notation and the same, let's say, integral expressions we have. So for that, we redraw the two plates. So let's redraw the two plates. But now I swap the roles, right? So as you can see, before so there are several ways to explain it, but I want to basically swap the roles. I basically want to swap the two plates, right? Because then the geometry and the path is the same. And then we can concentrate on the direction of the electric field and the displacement here along the path element. So that means what was negative now is positive. And why is this positive? Because we moved negative charges from here to here. So this is now negative. Negative charges are accumulated or moved, displaced to the other plate, right? So now we are basically moving negative charges from one place to the other. And again, the total charge, if you sum the charges on both plates, will be 0. And now the electric field would change its orientation, right? It's still in y direction, but now it's not anti-parallel to y, but parallel to y. So we still have the same point A where we start and the same point B where we end. We still have the same path S, right? So this is point A and point B, right? And this time we don't have a red particle, this time we have a blue particle. So now this is negative, right? And still we have this little tiny path vector. Here I draw it a little larger because then it's easier to read. So we have this at this little point. At this point here we have a little displacement ds, which we then have to integrate. So again, dx and dy. So now let's look at the work. Work is negative acting against the force ds from, let's say, along the path S, which is now negative q integral E ds. So what is EDS? As we said before, so where? Maybe here. So E ds is now E times the sum of dx and dy. And still, right, this is the electric field. You see, of course, the electric field and dx are still perpendicular. This component vanishes, which is then replaced, which is then reduced to E dy. So now let's discuss E dy. You see, the electric field is pointing upwards, and dy is also pointing upwards, which means, in our case, the assumption is that the electric field is now parallel to dy, which means that E dy is E dy times plus 1, right? Which is the cosine of 0 degrees, right? It's the plus 1, E dy. So that means it's E dy. So now let's look at W. W is now minus Q. And now, again, the same integration, right? Path S, we start at YA and end at YB. So same integration we did before is then E times dy, so delta y, right, which is the upper limit of the integration minus the lower limit of the integration. So the end point minus the start point, right, for this. So A would have the components xa and ya, and so the point A, right, and B accordingly, right, xb and yb. So these are the coordinates of these points. But since we are just walking, we just have to look at the scalar dy, right, which is in this direction. Good, which is then minus q e d. So what is this? Is this now negative? No, because I forgot to mention that the charge q we are talking about here, this little charge q, since it's a negative charge, is less than 0, minus 1 Coulomb. So that means in the end, since q is less than 0, this again is greater than 0, right? So you see the work is also positive because we have to invest our energy to move this particle or this charge against the repelling force exerted by this negative charge here and basically the positive charge here. That would be attracting, this would be repelling, and which means if you released this particle, it would move towards the positive terminals. Okay. So now let's go a step further. With our work, we are changing the potential energy. That's a change in potential energy, which is in our case Q times D, right, for this distance here, D. That's the path we are traveling in the y direction from point A to point B is exactly D. Or more generally, so this is for the very specific case we have here, but you can write this more generally. So this is true when it's positive, right? So more generally, W would be negative Q integral E ds, right? That is the most general expression. And the compensation of this negative here comes from the scalar product of E and ds. So this can be either greater than 0 if it's parallel, or less than 0 if it's antiparallel. And together with this sign, which can also be plus or minus in the Q, right? It can be greater, the charge itself can be larger or less than 0. The work becomes positive, always positive, when we apply the work to the system, and it always becomes negative when the work is done by the system. And then we introduce the potential. So this is the potential energy. So let me write it down here. So work is changing the potential energy. So if we do work on the system, we are increasing the potential energy of the system. If the work is done by the system, yeah, where does this work come from? It comes from the internal energy, which is then the potential energy. So by decreasing the potential energy of a system, you can use this released energy to do work. Okay. So then we introduce the potential. So what is this? A potential difference, dV, is the change in the potential energy per charge, right? So you can think of this being the change of potential energy per unit charge. So, which means in electrical engineering or in electronics, or if you look at your devices, right, we are talking about voltage, because this potential, so V is what we call potential. But in many contexts, we call this basically the voltage, or sometimes we call delta V the voltage difference, or so, potential or voltage. And the units, of course, the unit of the potential is volts. V, so volts. Or you can say, you can see this also from here, of course, the units of W is the same as the unit, so the unit of work is the same as the unit of potential energy, and energy is joule. So, and from this equation here, you can infer that the unit of delta V, of course, it's a difference between two potentials, potential difference of two voltages is the same as the unit of V, but you can see here it can also be expressed as joule, which is the change in potential energy per Coulomb. So the change of potential energy acting on a particular charge, right? Okay, which means that if you change the voltage of a system, right, or you have maybe a potential difference, you still don't know what the actual change in the potential energy would be, right? How much potential energy would be stored because of this potential difference here, this delta V, because then you have to know the Q you are talking about. And that will be an exercise which I will publish later. Thank you so much.